Another example on the modeling of electrical system, but this time he's asking me to use nodal analysis to find the transfer function of V out over Vn. The output is voltage, the input is voltage, so nodal analysis will be easier here. So the circuit is given here. We will convert it to Laplace, as you see here. So this quantity will be 2s. 2 Henry become 2s, 1 ohm become 1, 3 Henry become 3s, and 1 over 2 farad, I mean half farad, will be equal to 2 over s. We are going to assign node number 1 here. This is node number 1 and this is node number 2 as indicated, and we will apply the nodal analysis as you will see in the next slide. So at node 1, which shown here, we are going to apply Kirchhoff current law, where Kirchhoff current law is saying total current equal to 0. So we will evaluate this current, then this current, then this current, and their total equal to 0. That's what we will do in node 1. So at node 1 here, he said VR minus VI over 2S. VR minus VI over 2S, I mean this current minus this voltage minus this voltage divided by this impedance is going to be this current. Okay, now plus VR over 1, VR over 1, again VR over 1, which this current, plus VR minus VC over 3S, VR minus VC over 3S. Let me just make it clear here for the third element. For the third element, VR minus VC divided by 3S, that's going to be the current in the inductor. So all of them are equal to 0. So the total currents equal to 0. So this is one current, this is the other current, and this is the third current. Their total equal to 0. That's equation number 1. Now if I go to node number 2, we will apply the same technique, the same idea. So in node number 2, we have only two currents, which this current, the current in the 3S, and the current in the capacitor. So for the current in the 3S, it's equal to VC, look here, VC minus VR divided by 3S, okay, which this element. That's going to give me this current. And now this current, this current, how to get this current? For this current, it's equal to VC divided by the inductance, because it's divided by the capacitance, the impedance here. Because here there is no voltage, the voltage is 0 here, because this is the ground. So since the voltage is 0, it's VC minus 0 over 2S, over 2 over S. So when we write this one, it's going to look like this. So the two currents are equal to 0. That's how we can get the two equations. So the two equations are ready. Now we will deal with them mathematically. We will simplify them until we put them in certain format, which we can solve them by any technique, preferable Cramer's rule. So here he simplified the previous two equations and he put them in the form of coefficient VR, coefficient VC, and the output, which V. Okay, then from equation number 2, coefficient VR, notice here VR and here VR, I mean the arrangement, the right order in arrangement is very important. The right order in arrangement is very important to avoid any mistake in applying Cramer's rule. And coefficient of VC, if you notice here, VC with VC, VR, VR, and here constant, or in terms of constant or a value of a voltage. So when we have these two equations, we can solve them by Cramer's rule. So applying Cramer's rule, this is delta, which I explained it earlier. We calculate VR, and to apply Cramer's rule here, you can put them in this arrangement for VR and for VC. When you want to calculate VR and VC, I mean the two unknown in the two equations are VR and VC. We can calculate them, and we can solve. Finally, we find that V out over Vn is to be, by simplifying these two equations, we will simplify them, and finally they are going to look like this. So this is the transfer function. Again, I will remind you that this is considered as the mathematical expression describing that electrical circuit. This is the mathematical expression describing the electrical circuit, such that this electrical circuit look like system with equation in it. I mean, this equation going to be here, and it's having input and output. That's what we mean by modeling of electrical circuit or electrical network. Now we will talk about operation amplifier. Operation amplifier, we don't need to go to much detail. I am putting some introduction to operation amplifier, but you have idea about it. You have come across it before in instrumentation, in the course instrumentation. You attend to the operation amplifier. But here I need to know how to deal with it in terms of modeling. How am I going to deal with it in terms of modeling? Fortunately, operation amplifier is having fixed kind of transfer function, so we will just use it. You will see what I mean in the next slide. What's expecting in terms of operation amplifier? There are varieties of circuit. Each circuit will have its own transfer function. Here we are going to deal with inverting and non-inverting operation amplifier as example on the operation amplifier in general. If I have any operation amplifier circuit with its transfer function known, I'll be able to develop the whole transfer or the transfer function suitable for control system. Here we will start now with inverting amplifier in the next slide. This is the inverting amplifier, where in the inverting amplifier we are having input, notice input, then certain impedance, we call it the input impedance, which going to the inverting terminal. As I explained earlier, it's here that operation amplifier having inverting and non-inverting terminal. The negative means inverting, positive means non-inverting. Now, the input signal is going to go through Z1 to the inverting terminal. And feedback resistance or impedance, feedback impedance will go from the output, it will go from output back to the input. We have here Z2. It's very known to know the location of the impedances. That's why I'm describing it, because the impedances or impedance location is very important here. So I said earlier that the transfer function is developed already for the inverting amplifier. It's everywhere. Its transfer function will be minus Z2 over Z1. Minus Z2 over Z1. That means minus, don't forget this negative, minus of whatever impedance here, whether it's resistance or capacitance with resistance, whatever elements connected between output and input is considered as a Z2. Here divided by Z1, whatever element connected at the input. You will see this in the example after a while. Let us look at this example. Of course, as I told you, the transfer function is known. All what I need to know is identifying Z1 and Z2. So here in this example, he's asking me to calculate the transfer function V out over Vn for this system. This is V out and this is Vn. So V out over Vn is the output over input of inverting amplifier. This is inverting amplifier. So it's V out over Vn of the inverting amplifier. That means this is going to look, or this is going to be, this part, this impedance, going to be Z2, and this part is considered as a Z1. So we are going to calculate them, or put them in a simplified way. Then we will apply the equation which saying the transfer function is equal to Z2 over Z1. So Z1 is equal to 5 into 10 to the power 5. He mean here 5 into 10 to the power 5, 500K, 500K is 500,000, which means 5 into 10 to the power 5, plus, because they are in series, because as you see here, this resistor with this capacitor in series, so we just add them. So the value of the capacitor will be, this is, remember, it's 1 microfarad, 1 microfarad, so its Laplace equivalent will be 1 over, the Laplace of this one will be 1 over 1 micro S. Take this 1 micro up, it will become 10 to the power 6 as you see here. Okay, so that's it for Z1. Z2 we are going to calculate it by the same way, and then we will apply the transfer function equation, which Z2 over Z1, substitute the values, simplify, and finally this is the transfer function. Let me remind you again with this. Now to me, this circuit, to me I mean in terms of control, this circuit nothing but box or the model which having mathematical equation in it. The mathematical expression or equation in it is actually this one, with input equal to VI and output equal to Vout. Similar example here, you can deal with it. All what I want to tell you here is the impedance Z2 will be this one, this value, which equal to 100K. 100K, of course, in Laplace will be 100K, no problem. 1 microfarad will be 10 to the power 6 over S. They are in parallel. This element and this element are in parallel, both in series with this. That's for Z2. Now, Z1 is nothing but 100K in series with 1 micro, which will be again written as 10 to the power 6 over S. So after doing them, you can substitute them in this equation, substitute this value and this value in this equation, and you will find the transfer function as you see here. Non-inverting amplifier, let us describe the circuit here. In the non-inverting amplifier, the input will be connected to the non-inverting terminal of the amplifier, and the feedback resistance or impedance is connected between the output and the inverting terminal. That's how the configuration of the non-inverting amplifier is. The transfer function Vout over Vn is expressed as you see here. It's equal to Z1 plus Z2 over Z1. Always the transfer function equal to Z1 plus Z2 over Z1. So hopefully now you find that operation amplifier is something easy to deal with. All what I need to know is identifying the impedances, because I can apply the transfer function direct. You want to know Vout over Vn. We know that the equation. So all what I need to do is preparing Z2 and Z1. We will prepare these quantity. This is going to be Z2 and this is Z1. So Z2 is equal to 100K in series with this capacitor, and then Z1 equal to 200K in series with this capacitor. When we put them, this is Z1, this is Z2, substitute Z1 and Z2 in this equation, simplify, you will get the transfer function. So this is the transfer function, which again going to be input, output, and transfer function. That's all about the modeling of electrical system. In the next class, we are going to model more system. We are going to deal with translational mechanical system, rotational mechanical system, and electromechanical system. I hope you are clear about whatever we have studied. I wish you all the best. Thank you very much.